Have you ever wondered how evaporation works in industrial processes? It's a fascinating phenomenon that plays a crucial role in various sectors, from food and beverage to pharmaceuticals and even in the production of clean energy. But what exactly is evaporation? In the simplest terms, it's the transformation of a liquid into a gas, often under the influence of heat. But in an industrial setting, it gets a bit more complex. We'll be delving into the theory behind evaporation, understanding how evaporator capacity is determined, and exploring the delicate dance of heat and material balances. We'll also touch on the factors that influence heat transfer coefficients, a key component in the efficiency of the evaporation process. From pan to tubular and from wipe film to centrifugal rotary, we'll be discussing various types of evaporators and their subtypes, and even the accessories that make them work optimally. Ready to dive into the world of evaporation? Hold on tight as we embark on this exciting journey. Let's start with the basics. What is evaporation? In simple terms, it's the process by which water changes from a liquid to a gas or vapor. This is a fundamental phase transition that happens every day in nature and is also utilized in various industrial applications. But how does evaporation occur? It's all about energy. For water molecules to break free from their liquid state and become a gas, they need a certain amount of energy, known as the heat of vaporization. This energy can come from the surrounding environment or through direct heating. However, unlike boiling, where water turns into vapor at its boiling point, evaporation can occur at any temperature. This is because it's a surface phenomenon. Only the molecules with enough energy at the surface of the liquid can escape and become vapor. This also means that evaporation is a cooling process. As the most energetic molecules leave the liquid, the average energy of the remaining molecules decreases, leading to a drop in temperature. This is why you feel cooler when sweat evaporates from your skin. Now you might be wondering, how is evaporation different from boiling? While both processes involve a phase transition from liquid to gas, they occur under different conditions. Boiling happens throughout the liquid at a specific temperature and pressure, forming visible bubbles of vapor within the liquid. On the other hand, evaporation is a gradual process that occurs only at the surface of the liquid, without the formation of bubbles. Furthermore, the rate of evaporation is influenced by several factors, including temperature, pressure, surface area, and the presence of other substances in the liquid. For example, increasing the temperature or surface area can speed up evaporation, while adding a solute such as salt can slow it down. It's fascinating how such a simple process plays a vital role in our daily lives and various industries, from the water cycle that sustains life on Earth to the production of many consumer goods. Now that we understand the theory, let's explore how this applies in an industrial setting. In an industrial setting, how do we measure the capacity of an evaporator? That's a question that often pops up. To get the answer, we delve into the concept of evaporator capacity. Essentially, this refers to the amount of solvent that can be evaporated per unit time. In simpler terms, it's about how much stuff the evaporator can handle at once. Now you may wonder, why is this important? Well, evaporator capacity is crucial in determining the efficiency of the process. It helps engineers to design and select the appropriate equipment, ensuring that the evaporation process is as efficient and cost-effective as possible. So how do we calculate this capacity? It's all about the heat transfer. The capacity of an evaporator is directly related to the amount of heat that can be transferred from the heating medium to the evaporating solvent. This is where the concept of heat balance comes in. Heat balance, as the name suggests, is all about ensuring that the heat coming in equals the heat going out. In our context, the heat supplied should equal the heat absorbed by the solvent for evaporation, plus any heat losses. This balance is crucial in maintaining the efficiency of the evaporation process. But it's not just about heat. Material balance is another critical aspect. This involves tracking the amount and concentration of the solvent and solute throughout the evaporation process. It's like a meticulous inventory check, ensuring that what goes in equals what comes out, minus what's evaporated. Understanding and maintaining these balances, both heat and material, are fundamental to optimizing the evaporation process. They help to keep the process stable, efficient, and most importantly, predictable. So there you have it, a quick dive into the world of evaporator capacity and the heat and material balances. These concepts are the foundation of an efficient evaporation process. Now that we understand these concepts, let's look at the factors that influence heat transfer coefficients. What factors influence the efficiency of heat transfer during evaporation? That's the question we're here to answer in this segment. We know heat transfer is a critical aspect of evaporation. But did you know there are several factors that can impact how well this heat transfer takes place? Let's dive in and explore. The first key influencer is temperature. It's a pretty straightforward relationship here. The higher the temperature, the faster the heat transfer. This is because an increase in temperature leads to an increase in the kinetic energy of the molecules, which in turn speeds up evaporation. Next up, we have pressure. The pressure in the system can greatly affect the heat transfer process. Lower pressures can actually increase the rate of evaporation. This happens because at lower pressures, the boiling point of a liquid decreases. Hence, it's easier for the liquid to transform into a gas, leading to more efficient heat transfer. The third factor is the properties of the material being evaporated. Different substances have different specific heat capacities, which is the amount of heat required to raise the temperature of a specific amount of a substance by 1 degree Celsius. Materials with a higher specific heat capacity will require more heat to evaporate, impacting the efficiency of heat transfer. We also need to consider the surface area exposed to heat. A larger surface area allows for more heat to be absorbed, increasing the rate of evaporation. And finally, we have flow rate. In systems where the material being evaporated is flowing, the rate at which it flows can affect heat transfer. Faster flow rates can lead to more efficient heat transfer, as the material spends less time in the heat source, reducing the chance of overheating and degradation. In a nutshell, temperature, pressure, properties of the material, surface area, and flow rate all play a crucial role in determining the efficiency of heat transfer during evaporation. With a grasp on these factors, let's move on to the types of evaporators used in the industry. Did you know there are various types of evaporators used in the industry? Let's dive into the details. First up, we have pan evaporators. These are simple and economical. They are often used in the sugar industry and for other solutions that do not scale. The solution is simply boiled in the pan, and the vapor is sent directly to the condenser. Next, we have tubular evaporators. These come in several forms: horizontal, vertical short, and long. The horizontal type is used when dealing with solutions that have a tendency to foam. The vertical short and long tubular evaporators are ideal for heat-sensitive materials, as they allow rapid removal of vapor and have a short residence time. Diving deeper into tubular evaporators, we encounter subtypes such as rising film, falling film, and flooded evaporators. Each subtype has its specific use cases and advantages. For instance, the falling film evaporators are excellent for heat-sensitive, low-viscosity, or easily scale-forming solutions. Moving on, wipe film evaporators are a subtype of tubular evaporators. These are used for heat-sensitive or viscous solutions. The thin film allows for efficient heat transfer, while the wiping system prevents any buildup of residue on the heat transfer surface. Centrifugal rotary evaporators are next in line. They are used for concentrating heat-sensitive solutions and provide a gentle evaporation process by creating a thin film of the solution over a large surface area. Lastly, we have multiple effect evaporators. These are used when a high degree of evaporation is needed, and they are energy efficient as they reuse the heat from one effect in the next. They come in various arrangements like forward feed, backward feed, and mixed feed, depending on the specific requirements. Each of these evaporators has its unique features, offering a variety of solutions for different industrial needs. Whether you're dealing with heat-sensitive materials, viscous solutions, or scale-forming solutions, there's an evaporator type out there to meet your needs. Each evaporator type has its unique features. Now let's discuss some key evaporator accessories. What are the accessories that accompany an evaporator? Well, let's delve into that. Every evaporator system has a host of accessories that play crucial roles. First, we have the condensers. A condenser's job is to cool the vapor leaving the evaporator, turning it back into a liquid. This process is essential for maintaining the vacuum conditions needed for evaporation. Next, we have vacuum pumps. These pumps are necessary to maintain the low pressure in the evaporator, which enables the liquid to evaporate at lower temperatures. Then we have methods for removal of condensate. This process involves either steam traps or gravity draining, depending on the system. We also have entrainment separators. These devices remove droplets of liquid carried along with the vapor, ensuring the vapor is dry before it reaches the condenser. Last but not least, we have foam. Foam control is vital in evaporators to prevent carryover and ensure efficient operation. Understanding these accessories helps us appreciate the complexity of industrial evaporation processes. Now that we've covered the ins and outs of evaporation, let's summarize what we've learned. We've delved into the theory of evaporation, understood evaporator capacity, and dissected heat and material balances. We've explored factors that influence heat transfer coefficients and studied the varied types of evaporators and their subtypes. And let's not forget the essential evaporator accessories. It's a lot to take in, but remember, mastery comes with practice. Subscribe for more because you won't find me later. Stay curious and keep exploring.